Hello there, and welcome to Sealed, the channel where the largest questions are asked in the quietest possible voice, where science is allowed to slow down until it feels less like a lecture and more like a lullaby, and where the things we cannot fully understand are treated not as problems to be conquered, but as company for the night. Tonight, we are going to talk about an ending. Not a small ending, not the end of a story or a season or a life, but the end of everything. The end of the universe itself. The final, quiet closing of the longest chapter there has ever been or ever will be. It may sound like a heavy place to begin, but I promise you it isn't. Because the end of the universe, if the physics is right, does not arrive with fire or fury. It arrives slowly, gently, over spans of time so vast that they make the whole history of the Earth look like a single blink. And there is something deeply peaceful in that, something that might, strangely, help you rest. Before we drift out into that immense darkness, I'd love to know, where are you listening from tonight? Maybe you're somewhere warm, tucked beneath a blanket with the lights turned low. Maybe it's cold outside your window, and the world has gone quiet the way it only does late at night. Wherever you are, whatever the hour, I want you to know that you are held safely inside a universe that is, for now, still full of light. The ending we're going to imagine is unimaginably far away. You have nothing to fear from it. You are simply going to visit it, the way you might visit the edge of a shoreline, standing at the border of something enormous and calm. And if this kind of slow, spacious curiosity is the sort of thing that helps you unwind, I'd be quietly grateful if you'd like this video or subscribe to Sealed. It helps this small corner of the night reach other people who, like you, might be looking for a peaceful way to let the day go. There's no rush. There's nothing you need to do. Settle in, loosen your shoulders, let your breathing lengthen, and come with me out past the last of the streetlights, past the clouds, past the moon and the planets, out to where the story of the universe is still being written, all the way to its final page. Because everything ends. That is not a threat. It is simply the shape of things. Stars end. Galaxies end. The atoms in your body were forged inside stars that ended billions of years ago, and one distant day, unthinkably far from now, the last light in existence will end too. But between here and there lies a story so grand, so patient, so full of strange and beautiful stages, that to walk through it slowly is one of the most calming journeys the mind can take. So let us begin, not at the end, but here, in the middle of things, in the warm and crowded present, where the universe is young and bright and busy, so that we can understand just how far it still has to travel before it finally comes to rest. Let us start with the universe as it is tonight. Right now, at this very moment, you are living inside what astronomers sometimes call the stelliferous era, which simply means the age of stars. It is the age when the sky is full of light. And it is easy to assume that this is simply how the universe is, that stars are permanent fixtures, that the night sky has always looked more or less the way it looks now and always will. But that assumption is a kind of gentle illusion, born from the shortness of a human life. We are creatures who measure time in heartbeats and seasons, in mornings and evenings, in the slow turning of a single year. And against that scale, the stars do seem eternal. They were there when your grandparents were young. They were there when the first cities rose. They were there when the first humans looked up and began to wonder. So of course they feel like they will always be there. But they will not. The universe is not a fixed painting. It is a process, a slow unfolding, a river of change so gradual that we mistake it for stillness. And to understand its ending, we first have to understand that the bright, star-filled cosmos you were born into is not the default state of things. It is a phase, a luminous, fertile, extraordinary phase, but a phase all the same. And like all phases, it had a beginning, and it will have an end. Cast your mind out beyond the earth for a moment, beyond the sun, that warm and familiar star that anchors our days. Our sun is one star among perhaps 100 billion in the Milky Way, our home galaxy, a great slow wheel of light turning through the dark. And the Milky Way is one galaxy among perhaps 2 trillion in the observable universe. 2 trillion galaxies, each one a city of stars, each one drifting through the black with its own history, its own color, its own quiet fate. When you look up at the night sky and see a scattering of stars, you are seeing only the nearest few thousand of your own galaxy's inhabitants. The true scale of things is almost impossible to hold in the mind. It is not meant to frighten you. It is meant to be marveled at, softly, the way you might marvel at the sound of the sea in the dark. And here is the first strange and beautiful truth about the universe you live in. It is expanding, not into anything, not outward from a center, the way an explosion spreads through a room, but expanding within itself, everywhere at once, as though the very fabric of space were being gently stretched. The galaxies are not so much flying apart as being carried apart, riding on the slow swelling of space itself, like leaves resting on the surface of a lake that is quietly widening in every direction. Every distant galaxy is drifting away from every other. The more distant a galaxy is, the faster it recedes. And this is not a local quirk or a temporary motion. It is the fundamental behavior of the cosmos, woven into it from its earliest moments. This expansion is the key to everything that follows. It is the thread we will follow all the way to the end, because if space is stretching, then the universe of tomorrow is subtly larger, subtly emptier, subtly more spread out than the universe of today, and the universe of 1 billion years from now will be more spread out still. Run that forward far enough, patiently enough, and you arrive at a cosmos utterly unlike the one we know. A cosmos where the galaxies have drifted beyond one another's reach, where the sky, from any given world, has emptied of neighbors, where the light has thinned and thinned and thinned again, until at last there is almost nothing left to see. That is the road we are walking tonight. But we are only at its beginning, and the beginning is a place of abundance. For now, the universe is generous with its light. Stars are being born even as you rest. In the great clouds of gas and dust that drift between the stars, gravity is quietly gathering material together, pulling it inward, squeezing it tighter and tighter, until, deep in the heart of the collapsing cloud, the pressure and heat become so immense that a new star ignites. It is happening constantly, all across the galaxy, all across the 2 trillion galaxies of the cosmos. New suns are lighting up in the darkness, some of them destined to burn for only a few million years in brilliant, reckless splendor, others destined to smolder for trillions of years in patient red dimness. The universe, in this era, is fertile. It is creating. It is, in the fullest sense of the word, alive with light. But every star that is born draws down a little of the universe's finite supply of gas. Every act of creation spends something that cannot be fully replaced. The clouds of hydrogen from which stars are made are vast, but they are not infinite, and once a star has burned its fuel and died, much of the material it used is locked away, buried in dense remnants, or blown out into space in forms that will not easily gather into new stars again. Slowly, imperceptibly, across billions upon billions of years, the raw material for making stars is being used up. The universe is spending its inheritance, and though the inheritance is enormous, spending is spending. One distant day, the last of it will be gone. That is the quiet arithmetic that governs the fate of everything. Expansion spreads the universe thin, star formation spends its fuel, and time, patient and unhurried, carries both processes forward, without pause and without mercy, though also without malice. The universe is not ending because anything is going wrong. It is ending because it is running exactly as it should, following the same simple laws that light your sun and warm your face on a summer afternoon. The ending is written into the beginning. It always was. So hold that thought gently as we go. The bright sky above you is not a permanent thing. It is a golden hour in the life of the cosmos, a long and luminous afternoon that will, in its own unhurried time, fade into evening, and you are here for it. Of all the eras the universe will ever pass through, of all the trillions upon trillions of years still to come, you happen to open your eyes during the age of stars, during the age of light, during the one brief window when the sky is full. That is not something to mourn. That is something to feel quietly lucky about as you drift toward sleep beneath a sky that still remembers how to shine. Now, to truly follow the universe to its ending, we have to understand the single most important discovery in the story of its fate, because for a long time, we did not know which way the story would turn. For most of human history, we did not even know that the universe had a story at all. We imagined it as fixed, eternal, unchanging, a stage that had always existed and always would. And it was only within the last 100 years, a mere flicker of time, that we learned the truth. That the universe has an age, that it has a history, and that it is going somewhere. The first crack in the old idea of an eternal, static cosmos came in the early 20th century, when astronomers began to measure the light of distant galaxies with real precision. When you spread the light of a star or a galaxy out into its colors, the way a raindrop spreads sunlight into a rainbow, you find dark lines threaded through it, fingerprints left by the elements within, and those fingerprints, those patterns of lines, were showing up in the wrong place. In galaxy after galaxy, they were shifted toward the red end of the spectrum, stretched to longer wavelengths, as though the light itself had been pulled and lengthened on its long journey to us. This was the redshift, and the further away a galaxy was, the more its light was shifted. The pattern was unmistakable. The galaxies were receding, and the distant ones were receding fastest of all. There was really only one sensible way to explain it. Space itself was expanding, carrying the galaxies apart. And if the universe is expanding today, then yesterday it was smaller, and the day before smaller still. Wind the film backward, patiently, billions of years at a time, and everything draws closer and closer together, hotter and denser, until it converges on a single, unimaginably compact and fiery beginning. This was the origin of what we now call the Big Bang, the idea that the universe began, some 13.8 billion years ago, in a state of extraordinary heat and density, and has been expanding and cooling ever since. Not an explosion in space, but an expansion of space, an unfurling that is still going on, all around you, tonight. For a while, though, an important question remained open, and it is the question that decides how everything ends. The universe is expanding, yes, but gravity is always pulling. Every galaxy tugs on every other galaxy, gently, across the void. And gravity, given enough time, could in principle slow the expansion down, and perhaps even halt it, and perhaps even reverse it. So the great question of cosmic destiny came down to a kind of tug-of-war. On one side, the outward momentum of expansion, the universe's inheritance of motion from its fiery birth. On the other side, the inward pull of all the matter it contains, patiently trying to draw everything back together. Which one would win? Would the universe expand forever, thinning into cold and dark? Or would gravity eventually triumph, pulling everything back into a final collapse? For decades, astronomers did not know. The fate of everything hung in the balance, waiting to be measured. And then, in the closing years of the 20th century, came a discovery so surprising that the astronomers who made it could hardly believe their own results. They had set out to measure how quickly the expansion of the universe was slowing down. They fully expected it to be slowing, gently braked by the gravity of all the matter within it. The only question, they thought, was how much. So they looked far out into space, and therefore far back in time, using a particular kind of exploding star as a measuring rod, a beacon whose true brightness they understood, so that its apparent dimness could tell them exactly how far away and how far back it lay. They gathered their light, and they did their sums, and they waited for the universe to reveal how much it had slowed. It had not slowed at all. It was speeding up. The distant explosions were fainter than they should have been, which meant they were further away than expected, which meant the expansion of the universe, far from being gently braked by gravity, had actually been accelerating, not slowing, not coasting, accelerating, pushing the galaxies apart faster and faster as time went on. It was as though you had thrown a ball into the air, expecting it to slow and fall back to your hand, and instead watched it rise faster and faster, climbing away into the sky under some invisible push. Something was overpowering gravity across the vast reaches of space. Something was driving the universe apart with a force that grew stronger, in effect, as space itself grew larger. We do not fully understand what that something is. We have given it a name, dark energy, but the name is really just a placeholder for our ignorance, a polite way of saying that there is a mysterious energy woven into the fabric of empty space, an energy that pushes outward, that never dilutes away as the universe expands, that seems to be a property of the vacuum itself. Empty space, it turns out, is not truly empty. It has a faint, restless energy of its own, and that energy has a subtle repulsive effect, a gentle anti-gravity that spreads across every cubic meter of the cosmos. When the universe was young and small and crowded, gravity had the upper hand, and the expansion slowed. But as the universe grew, and the matter within it thinned out, the pull of gravity weakened, while the push of dark energy, being a property of space itself, held steady and then took command. Some 5 or 6 billion years ago, roughly around the time our own sun and earth were forming, dark energy won the tug of war, and from that moment on, the expansion of the universe has been accelerating, and it is accelerating still. This is the discovery that decides the ending, because if dark energy behaves the way our best measurements suggest, then the great question of cosmic fate has been answered. The universe will not collapse back on itself. It will not be pulled together into a final fiery crunch. Instead, it will expand forever, faster and faster, spreading thinner and colder and darker across an eternity of time. The galaxies will drift apart, the light will fade, and the cosmos will settle, slowly, over spans of time that dwarf all the numbers we know, into a vast, cold, quiet emptiness. This ending has many names. Some call it the Big Freeze. Some call it the heat death. But whatever we call it, it is the destination toward which the accelerating expansion is carrying us, and it is the main path we will walk tonight, gently, one stage at a time. But before we set out along that path, hold this in mind, because it is a comfort rather than a sorrow. The ending is not soon. It is not even close to soon. The universe is 13.8 billion years old, and that already feels like an eternity. Yet against the time scale of the ending, 13.8 billion years is nothing. It is the first faint stirring of dawn in a day that will last for numbers we can barely write down. Everything we are about to describe lies so unimaginably far in the future that the whole of cosmic history so far, every galaxy that has formed, every star that has lived and died, every world and every mind, occupies only the tiniest sliver at the very beginning. We are near the start of a story so long that its ending is almost a myth. So there is no need for grief tonight. There is only the slow, spacious pleasure of following a river all the way to a sea that no one will ever quite reach. Let us begin, then, to walk forward in time. Not in years, for years will soon become useless, too small to measure the ages we are entering. We will walk instead in great leaps, each one carrying us far beyond the last, watching the universe change as we go. And our first destination is the slow fading of the age of stars. Come forward with me, then, past the present, past the near future, past a time so distant that the constellations you know tonight have long since dissolved and reformed into shapes no human eye will ever see. The stars are not fixed. They drift, each on its own long orbit around the center of the galaxy, and over hundreds of millions of years the familiar patterns of the night sky smear and scatter and rearrange themselves entirely. The plow, the hunter, the whole quiet architecture of the constellations, all of it is temporary, a passing arrangement of drifting lights. Give it enough time, and every pattern you have ever learned will be gone, replaced by others, which will in turn dissolve. Nothing in the sky holds its shape. It only holds it long enough to seem still to us. But we are traveling much further than that tonight. We are going to a time when the very business of making stars begins to wind down. Remember the quiet arithmetic. Every star that forms spends some of the universe's finite supply of gas, and though the supply is vast, it is being drawn down, steadily, galaxy by galaxy, age by age. The rate of star formation across the cosmos actually peaked long ago, some 10 billion years in the past, in the universe's fiery youth, when great floods of fresh gas poured into forming galaxies and lit them up in a blaze of new suns. Since then, the rate has been declining. The universe is past its peak of creation. It is, in the gentlest possible sense, growing old. Not frail, not dying, simply mature, its most fertile years behind it, settling into a long, slow, luminous middle age. Fast forward, and the decline continues. The great bright stars, the massive blue giants that burn furiously and die young, become rarer and rarer, because there is less and less fresh gas to make them from. What remains, more and more, are the small, faint, patient stars, the red dwarfs. And here is one of the most beautiful and calming facts in all of astronomy. The smaller and dimmer a star is, the longer it lives. The great showy stars burn out in a few million years, spending their fuel in a reckless blaze. But the little red dwarfs, cool and dim and frugal, sip their fuel so slowly that they can shine for trillions of years, far longer than the entire current age of the universe. They are the tortoises of the cosmos, the long-distance runners, the ones who will still be quietly glowing long after every brilliant giant has gone dark. So imagine the universe as it ages. The bright stars fade from the story, one by one, with no new giants to replace them. And what is left is a sky of red dwarfs, dim and rust-colored and enduring, scattered across galaxies that have grown quiet and dark. If you could stand on a world beneath such a sky, in that far-off age, you would see a very different night than the one above you now. Fewer stars, dimmer stars, a cosmos settling toward a deep, warm, ember-like glow, like a fire that has burned down from leaping flames to a bed of coals, still giving light, still giving heat, but softer now, and slower, and closer to rest. There is something worth pausing on here before we travel further. As the universe ages and expands, another slow change is taking place in the sky, one that will shape everything that comes after. The galaxies are drifting apart, and because the expansion is accelerating, they are drifting apart faster and faster, carried away on the widening of space. This means that, over enormous spans of time, the distant galaxies will recede from one another until they pass beyond reach entirely, beyond the point where even their light can bridge the gap. One by one, over billions of years, the far galaxies will slip over a kind of cosmic horizon, their light stretched and dimmed and finally lost, until at last, from the vantage point of any single galaxy, the rest of the universe will simply have vanished from view. Think of what that means for the sky of the far future. Tonight, on a clear, dark night, far from city lights, you can just make out the faint smudge of the Andromeda Galaxy, a whole other island of hundreds of billions of stars, 2.5 million light-years away. It is the most distant thing the unaided human eye can see. But in the deep future, no such neighbor will be visible from anywhere. The galaxies will have drawn apart. Any inhabitants of that far-off age, looking up, would see only their own galaxy, an island of light adrift in an ocean of perfect black, with no sign that anything else had ever existed. They would have no way of knowing that the universe had once been full of galaxies, no way of discovering the expansion, no way of reconstructing the Big Bang. The evidence would have receded beyond their horizon. The story of the cosmos would have quietly erased its own opening chapters. There is a strange poignancy in that, and also a strange comfort. We are living in a time when the universe still remembers its own beginning. when the galaxies are still close enough to reveal the truth. We can see the story. The ones who come after may not. Before we travel that far, though, let us pause a little closer to home, because the great cosmic ending has smaller endings nested inside it, and some of them belong to us. Long before the last star fades, long before the galaxies drift beyond one another's reach, our own small corner of the universe will pass through changes of its own, and there is a gentle beauty in them worth dwelling on for a moment. Consider our sun, that steady golden star that has warmed the Earth for 4.5 billion years and will warm it for billions more. It too is living out a story with an ending. Right now the sun is in the prime of its life, quietly fusing hydrogen into helium in its core, holding itself in perfect balance between the crush of its own gravity and the outward push of its warmth. This balance has held since before the first life stirred on Earth, and it will hold for a long time yet. But the sun is slowly, imperceptibly changing. It is growing gradually brighter as it ages, and in something like 1 billion years, its rising warmth will begin to make the Earth uncomfortably hot, boiling away the oceans, transforming our blue world into something dry and strange. And in about 5 billion years, the sun will finally exhaust the hydrogen at its core, and its long, graceful death will begin. When that time comes, the sun will not explode. It is not massive enough for that. Instead, it will swell. Its outer layers will billow outward, and it will grow into a vast, cool, red giant, swallowing the innermost planets, perhaps reaching as far as the Earth's own orbit, its bloated surface glowing a deep and gentle red. And then, in its final act, the dying sun will cast off those outer layers entirely, breathing them out into space, in a soft, luminous, expanding shell, a thing of astonishing beauty, a glowing veil of gas, drifting outward against the dark. At the center of that veil, all that will remain of our sun is its exposed core, a small, dense, brilliantly hot white dwarf, no longer burning, only glowing with the leftover warmth of a star that shone for 10 billion years. And that white dwarf will then begin the long, slow cooling we have already imagined, fading across the aeons from white to red to a final, distant dark. Our sun, in the end, will become one of those cooling cinders drifting through the degenerate era. Its story and the story of the universe are the same story, only told on different scales. There is another great change coming to our local sky, even sooner than the sun's death, and it is not an ending but a merging. Our galaxy, the Milky Way, is not alone. Its nearest large neighbor, the Andromeda Galaxy, that faint smudge you can just glimpse on a clear dark night, is not receding from us like the more distant galaxies. It is falling toward us, drawn by gravity across the gulf of 2.5 million light-years, closing the distance at a steady, patient pace. And in roughly 4 to 5 billion years, around the same era as the sun's transformation, Andromeda and the Milky Way will meet. They will not so much collide as flow through one another, two great wheels of stars passing and mingling, their shapes torn and reshaped by the slow pull of gravity over hundreds of millions of years. The stars themselves are so far apart that almost none of them will actually strike one another. The two galaxies will pass through each other more like two clouds merging than two solid objects crashing. But the encounter will scramble both galaxies utterly, flinging long streamers of stars out into the dark, and eventually, over 1 billion years or so, the two will settle together into a single, larger galaxy, an elliptical swarm of stars that astronomers have already, fondly, given a name. They call it Milkometa, the child of the Milky Way and Andromeda, the galaxy our descendants, if any exist, might one day call home. If any watchers survive on some far future world to witness that merging, they will see one of the most spectacular skies imaginable, two galaxies filling the heavens, their arms wrapping and unwinding across the night, a slow cosmic dance unfolding over spans of time longer than complex life has existed on Earth. It is a reminder that even the largest and most seemingly permanent structures in the sky are in motion, are changing, are living out their own long stories of gathering and merging and dissolving. Nothing holds still. Not the constellations, not the galaxies, not the sun, not the earth. Everything is drifting, changing, becoming something else, on timescales so vast that we mistake the motion for stillness. And all of it, the sun's death, the galaxies merging, the slow fading of the stars, is carrying the universe, step by patient step, toward the ending we have come here to imagine. But let us return to the fading of the stars and travel forward again, further than before, far beyond the death of the sun and the merging of the galaxies, into a time when even these local dramas have long since played out and been forgotten. We are now approaching a threshold, an ending within the greater ending. There comes a time, unimaginably distant, when the last of the star-making gas is finally spent, when the great clouds have all collapsed, and their material has been locked away in stars, and those stars have burned through their fuel, and no new clouds remain from which fresh stars could form. When that time comes, star formation ceases altogether. The last new star is born. It happens, according to our best estimates, somewhere around 100 trillion years from now. 100 trillion. Write it out, and it is a 1 with 14 zeros after it. It is a number so large that if you tried to count to it, one number every second, you would need millions of times the current age of the universe just to finish counting. And yet, in the grand story of cosmic endings, 100 trillion years is still early. It is still, remarkably, near the beginning. When the last star is born, the age of stars is not quite over, because that final star will go on shining for a long while yet, and the red dwarfs already burning will continue their patient glow for trillions of years more. But the creative age is finished. No more new suns will ever ignite. The universe has spent the last of its inheritance of light-making gas, and from here on, it can only spend down what already burns. The lights are still on, but no one is lighting any new ones. And so, slowly, one by one, over an almost incomprehensible span of time, the stars begin to go out. The great red dwarfs are the last to fade. These frugal little stars, sipping their fuel so slowly, will still be glowing when the universe is thousands of times older than it is today. But even they cannot burn forever. Eventually, each red dwarf exhausts its fuel and cools, dimming from red to a deep, dull ember to darkness. And when the last red dwarf finally winks out, somewhere on the order of 100 trillion years from now, or a little after, the age of stars comes to its true and final close. The sky goes dark. Not the ordinary dark of night, which is only the earth turning its face from the sun, but a deeper dark, a permanent dark, the dark of a universe in which no star anywhere is shining. That is the end of the stelliferous era. That is the end of the age of light, and it is the beginning of a new age, a stranger and quieter one, which astronomers call the degenerate era. Do not let the word trouble you. In this context, degenerate does not mean anything corrupt or fallen. It is a technical term borrowed from physics, describing the peculiar, ultra-dense state of the matter that remains once the stars have died. For when a star burns out, it does not simply vanish. It leaves something behind, a remnant, a dense, cooling core, the compressed ash of a star that once shone. And in the degenerate era, these remnants are all that is left. The universe becomes a vast, dark, silent cemetery of dead stars, drifting through emptiness, slowly cooling toward the cold of deep space. Let us go there, gently, and see what remains. When a star like our own sun exhausts its fuel, it does not explode. Instead, in its final act, it swells enormously into a red giant, shedding its outer layers into space in a soft, glowing shell, and leaving behind its core a small, dense, incredibly hot object called a white dwarf. A white dwarf is a strange and wonderful thing. It packs a mass comparable to the sun into a ball roughly the size of the Earth. A single teaspoon of white dwarf material would weigh several tons. It no longer burns any fuel. It simply glows with leftover heat, radiating its warmth slowly away into the dark. And because it has no fuel to burn, it can only cool. Over billions upon billions of years, a white dwarf fades from brilliant white to yellow to red to a deep, dim ember, and finally, in theory, to a cold, dark, crystalline cinder, a black dwarf, invisible against the black of space. This cooling is so slow that, at the present age of the universe, not a single white dwarf has had time to cool all the way to darkness. The universe is simply not old enough yet. Every black dwarf that will ever exist still lies in the future. More massive stars leave behind stranger remnants still. When a star much heavier than the sun reaches the end of its life, it dies not with a quiet fading, but with a colossal explosion, a supernova, one of the most violent events in all of nature, briefly outshining an entire galaxy. And in the heart of that explosion, the star's core is crushed inward with such unimaginable force that it collapses into something even denser than a white dwarf, a neutron star. A neutron star squeezes more than the mass of the sun into a sphere only a dozen or so kilometers across, roughly the size of a city. Its matter is so dense that a single teaspoon of it would weigh as much as a mountain, perhaps as much as all the humans who have ever lived combined. Neutron stars spin, sometimes hundreds of times a second, sweeping beams of radiation across the cosmos like lighthouses in the dark. And like white dwarfs, they slowly cool, radiating their heat away, dimming across the ages toward cold and silent stillness. And then there are the black holes. When the very heaviest stars die, their cores collapse so completely that nothing can hold them up, and they fall inward without limit, crushing down to a point of such extreme density that they warp the fabric of space and time around themselves, creating a region from which not even light can escape, a black hole. These are the darkest, strangest objects the universe produces. Gravitational whirlpools sealed off from the rest of existence by a boundary called the event horizon, beyond which everything falls in and nothing returns. In the degenerate era, black holes are simply another kind of remnant, another form of stellar ash, scattered through the dark alongside the white dwarfs and neutron stars. But hold them in mind, because their story does not end here. Long after the white dwarfs and neutron stars have played out their parts, the black holes will inherit the universe. Their age is still to come. So picture the degenerate era in full. The stars are gone. In their place drift the remnants, countless white dwarfs, slowly cooling from ember red toward final black. Neutron stars, dense and silent, their spin gradually winding down. Black holes, dark and patient, warping the space around them. And between these remnants, an ever-widening emptiness, for the universe is still expanding, still stretching, still carrying everything further apart. The galaxies themselves have changed too. Over these enormous spans of time, the orbits of stars within a galaxy slowly decay and rearrange, some remnants flung out into the intergalactic void, others spiraling inward toward the great black holes that lurk at galactic centers. The neat spiral shapes we admire in photographs tonight will long since have dissolved. What remains are loose, dark swarms of dead stars, thinning out, drifting apart, growing ever quieter. And yet, even in this dark age, the universe is not entirely without events. Every so often, across the vast emptiness, two of these dead remnants will happen to drift close to one another. Two brown dwarfs, perhaps, those failed stars that never quite grew massive enough to shine, might collide and merge, briefly gathering enough mass to ignite, flickering into life as a genuine star for a few million years before fading again. In the deep dark of the degenerate era, such rare collisions might be almost the only stars left, sparking into being here and there across the cosmos, tiny brief candles lit by chance, burning for a geological instant, and then going out. If any watchers remained to see them, they would be the rarest and most precious lights imaginable, single stars glowing alone in galaxies of the dead. But such collisions are extraordinarily rare, growing rarer as the remnants drift further apart, and they cannot hold back the tide. The universe is cooling, darkening, emptying. The age of stars is a memory. The age of remnants has begun. Let us dwell here a little, in the degenerate era, because it lasts an astonishingly long time, and because there is a strange peace in it. Imagine drifting through this dark cosmos. There is no light to see by, or almost none, only the faint dimming glow of cooling remnants, growing fainter century by century, aeon by aeon. There is no sound, for space has always been silent. There is only the slow, patient cooling of matter, the gentle widening of space, and time, endless time, flowing forward without event. If the age of stars was the universe's bright and busy afternoon, the degenerate era is its long, quiet, deepening dusk, a dusk that lasts not for hours, but for spans of time so vast that the entire history of stars, from the first ignition to the last fading ember, is only a brief opening scene by comparison. But even remnants do not last forever. Even the dead stars are subject to change, though the changes come with a slowness that defies imagination. And to understand what happens next, we have to descend into the very heart of matter itself, into the tiny particles from which everything is built, and ask whether they too must one day come undone. Everything you have ever touched, everything you have ever seen, your own body, this world, the remnants drifting through the far future, all of it is made of atoms. And atoms are made of smaller things still, of electrons whirling around a dense central nucleus. And that nucleus is built from particles called protons and neutrons. These are the fundamental building blocks of ordinary matter, the tiny bricks from which the entire visible universe is assembled. And for most of the history of physics, we assumed they were eternal. We assumed that a proton, once formed, would simply last forever, unchanging, a permanent fixture of reality. Rocks might crumble, stars might die, but the protons themselves, we thought, would endure without end. But some of our deepest theories of physics whisper otherwise. They suggest that even the proton, that most stable of particles, may not be truly eternal, that given enough time, an unimaginable stretch of time, a proton might spontaneously decay, breaking apart into smaller particles and radiation, quietly ceasing to be. We are not certain this happens. We have searched for it in vast underground experiments, watching enormous tanks of water for the faint flash of a single proton coming undone, and so far we have never caught one in the act. This tells us that if protons do decay, they do so with extraordinary rarity, on timescales so long that in any human lifetime, in any ordinary volume of matter, you would essentially never see it. But rarity is not the same as never, and if protons do decay, even with almost unthinkable slowness, then the consequences for the far future are profound. For if protons can decay, then all ordinary matter is living on borrowed time. Every white dwarf, every neutron star, every cold dark cinder drifting through the degenerate era, every remnant of every star that ever shone, is made of protons and neutrons that are, ever so slowly, coming apart. Over spans of time estimated at something like 10 to the power of 34 years, or 10 to the power of 34 years, or longer, numbers with 30 and 40 zeros, the matter of the universe would gradually dissolve. The white dwarfs would slowly evaporate, not by burning, but by the quiet disappearance of their own particles. One by one, each proton decay, releasing a tiny puff of energy, so that these dead stars would glow, ever so faintly, with the light of their own dissolution. A white dwarf in this era would radiate a warmth fainter than you can imagine, a glow dimmer than a distant candle across an ocean, powered not by fusion, but by the slow unraveling of matter itself. And over these vast stretches, the remnants would shrink and fade and finally vanish, their substance returning to simpler particles and radiation, scattered thin across the ever-expanding dark. This is one of the strangest thresholds in the whole story of the ending. It is the point at which ordinary matter, the stuff of worlds and bodies and stars, ceases to exist as a meaningful thing. If proton decay is real, then there comes a time, unimaginably far in the future, when there are simply no atoms left anywhere in the universe, no solid matter of any kind, no white dwarfs, no neutron stars, no planets, no dust, Nothing that could be called a thing in the way we mean it. Only a thin, cold soup of elementary particles, electrons and their antimatter counterparts, and photons of light, and the ghostly, nearly weightless particles called neutrinos, all of it spread across a cosmos grown vast and empty almost beyond comprehension. The matter era is over. The universe has forgotten how to be solid. But I said we are not certain protons decay, and that uncertainty opens up a second possibility, a different path to a similar end. Perhaps protons are truly stable, truly eternal, and never decay at all. If so, the white dwarfs and neutron stars would not dissolve in the way I have just described. They would simply drift on, cold and dark, essentially forever, waiting for some other process to claim them. And there is such a process, subtler and slower even than proton decay, a process that would, given enough time, turn even the most stubborn cold cinder into a black hole, through the almost inconceivably rare quantum rearrangement of its particles. On timescales so long, they make proton decay look hasty, numbers with not 30 or 40 zeros, but many more. Even solid matter would find a way to collapse and vanish. By one road or another, whether quickly through proton decay or slowly through these deeper processes, the ordinary matter of the universe is destined to disappear. The only question is how long it takes, and the answer, in every case, is longer than the mind can hold. Whichever path the universe takes, the destination is the same. The remnants fade, the matter dissolves or collapses. And when the last white dwarf has evaporated, when the last neutron star has come undone or crushed itself into darkness, the degenerate era ends. The dead stars are truly dead now, not merely dark but gone, their substance returned to the void. And what remains to inherit the universe are the only structures still standing, the last great fortresses of the cosmos, patient and immense, and darker than anything else that exists, the black holes. Their long reign is about to begin. We have traveled a long way tonight, further into the future than most minds ever wander, and still we are only partway through the story. So let your thoughts stay slow and soft. Let the numbers wash over you without needing to be grasped, and come with me into the age of black holes, the black hole era, the longest and darkest and, in its own strange way, most beautiful stage of all. By now, the universe has changed almost beyond recognition. The stars are gone. The remnants are gone. The atoms themselves have largely dissolved. Space has expanded to a scale that makes the present universe look impossibly cramped and cozy by comparison. Whatever galaxies once existed have long since dispersed, their dead stars flung apart or swallowed, and across the immense cold emptiness, there drift only the black holes. Some are the corpses of individual stars, a few times the mass of the sun. Others are the truly colossal ones, the supermassive black holes that once lurked at the centers of galaxies, containing the mass of millions or billions of suns, grown vast over the ages by swallowing everything that fell within their reach. In the black hole era, these are the last significant objects in existence. Everything else has faded. Only the black holes remain, silent and enormous, ruling over a cosmos of almost perfect emptiness. You might imagine that black holes, being the ultimate one-way doors, the objects from which nothing escapes, would simply last forever, eternal and unchanging, the final permanent features of a universe that has lost everything else. For a long time, that is exactly what physicists believed. A black hole seemed like the closest thing to true permanence that nature had ever made. But then came one of the most surprising and beautiful insights in the history of science, the realization that black holes are not truly eternal, that they too must one day die, that even these great fortresses of darkness are slowly, imperceptibly, leaking themselves away into the void. The idea came from thinking carefully about the strange behavior of empty space at the very edge of a black hole, at the event horizon, that boundary of no return. Empty space, it turns out, is not perfectly empty even here. On the tiniest scales, the vacuum seethes with a faint quantum restlessness, with pairs of particles flickering briefly into existence and then vanishing again, borrowed for an instant from the energy of the vacuum itself. Almost always, these pairs appear, meet, and annihilate, leaving no trace, and the vacuum stays as it was. But right at the edge of a black hole, something remarkable can happen. Occasionally, one member of such a pair falls across the event horizon into the black hole, while the other escapes, drifting away into space. To the distant universe, it looks as though the black hole has emitted a particle, and that escaping particle carries away a tiny sliver of energy, which means, because energy and mass are two faces of the same thing, that the black hole has lost a tiny sliver of its mass. The black hole, ever so faintly, is glowing. It is radiating. It is evaporating. This faint glow is called Hawking radiation, after the physicist who first worked it out, and it changes everything about the fate of black holes. Because if a black hole is slowly radiating its mass away, then given enough time, it must eventually radiate all of it away. It must shrink, it must fade, and at last, it must disappear entirely. Black holes are not eternal after all. They are simply the slowest dying things in the universe, so slow that their deaths take spans of time compared to which everything that came before is a mere flicker. And the speed of this evaporation depends, wonderfully, on size, but in a way that runs against ordinary intuition. Small black holes evaporate faster, glowing more brightly, radiating their mass away more quickly. Large black holes evaporate more slowly, glowing so faintly that their radiation is almost inconceivably weak, colder than the coldest thing you could ever measure. A black hole formed from a single dead star, a few times the mass of the Sun, would take something like 10 to the power of 64 years to evaporate completely. That is a 1 followed by 64 zeros. And the truly enormous ones, the supermassive black holes that once anchored galaxies, containing billions of solar masses, would take vastly longer still, on the order of 10 to the power of 100 years, a number called a googol, a 1 with 100 zeros trailing behind it. These are the longest-lived structures the universe will ever contain. They are its final monuments, its last standing stones, glowing so faintly that across almost the entire span of their existence, they are indistinguishable from the perfect dark around them. Let us pause here, in the presence of these numbers, and try, gently, to feel them, not to grasp them, for they cannot be grasped, but simply to sit beside them for a moment, the way you might sit beside a very deep and very still lake. When we say the universe is 13.8 billion years old, that number is already far too large for the mind to truly hold. A single billion years is beyond imagining. If you tried to live through a billion years, experiencing 1 year every second, you would be counting for more than 30 years without pause, just to reach the end. And the universe has lived through nearly 14 of those billions. That is the entire history of everything so far. Every galaxy, every star, every world, every story ever told, all of it fitting inside those 14 billion years. Now set that number, enormous as it is, against the timescales of the ending. The last star will fade in something like 100 trillion years. That is not 14 billion, but 100,000 billion, more than 7,000 times the current age of the universe. And that is only the beginning of the deep future. The black holes will reign for far longer, evaporating across spans measured not in trillions of years, but in numbers with 60, 80, 100 zeros. To write out the lifetime of the largest black holes, you would write a 1 and then 100 zeros, and every single one of those zeros represents another tenfold leap into the unimaginable. There is no meaningful way to picture such a span. It is not merely a very long time. It is a length of time so vast that the entire history of the universe up to this moment, all 14 billion years of it, is smaller against it than a single heartbeat is against the whole age of the Earth. If you gathered every second that has ever passed since the Big Bang, they would not amount to even the faintest sliver of the time the black holes will endure. And yet, here is the strange and calming truth. All of that time is coming, whether or not anyone is there to count it. The universe is patient beyond all patience. It does not hurry through its ages the way we hurry through our days. It has, quite literally, all the time there could ever be. There is no clock ticking against it, no deadline pressing upon it, no sense in which it is running late. It simply unfolds, one unimaginable age after another, in perfect unhurried calm, taking 100 trillion years to burn out its stars, and a Google years to evaporate its black holes, and never once feeling rushed, because rushing is a thing that only anxious, short-lived creatures do. The cosmos does not know anxiety, it only knows unfolding. There is something deeply restful in that, if you let it settle over you. All the urgency of a human life, all the pressure of the hours, all the feeling that there is never quite enough time, softens against a backdrop this vast. The universe will spend more time simply cooling and resting than it ever spent burning and shining. Stillness, not activity, is the natural long-term state of things. The bright and busy age we live in is the exception. The brief, exciting overture, the long calm that follows, is the far greater part of the song. So when the night feels short, when the day feels rushed, when there seems to be too little time for all the things you carry, remember the black holes glowing faintly in the dark for 100 zeros worth of years, in no hurry at all, and let a little of their patience become yours. So imagine the black hole era in its long, patient fullness. A universe grown unimaginably vast and cold and empty. Here and there, separated by distances that beggar all description, drift the black holes, each one utterly alone, each one slowly, silently evaporating, giving up its mass one faint particle at a time, across spans of time that make the age of stars look like a single spark. For most of this era, almost nothing happens. There is only the black and the emptiness and the black holes, and the slow, slow ebbing of their substance into the void. If the degenerate era was the universe's long dusk, the black hole era is its deep night, a night so long that all the previous ages of the cosmos combined would not fill even its opening moments. And then, at the very end of a black hole's life, after eons upon eons of faint, patient glowing, something changes. As the black hole grows smaller, its evaporation speeds up. It glows a little brighter, radiates a little faster, shrinks a little quicker, and this feeds on itself, accelerating, until in its final moments, the black hole is no longer the coldest thing in the universe, but suddenly the hottest, blazing up in a last brilliant flash as the remainder of its mass pours out in a burst of radiation. After 100 years, or a Google years, of near-perfect silence and dark, the black hole ends not with a whimper, but with a final flare of light, a last small firework in the endless dark, and then it is gone. Whatever fell into it across all those aeons, whatever it was made of, whatever it swallowed, all of it is returned to the universe at last, not as matter, but as radiation, thin and cold and scattered, spreading out across the void. The black hole has died, and with the death of the last and largest black hole, somewhere around 10 to the power of 100 years from now, the black hole era comes to its close. There is something almost tender in that final flash, when you sit with it. These objects were the darkest things the universe ever made, sealed off, silent, swallowing all that came near them. And yet at the very end, each one gives everything back. Every black hole, no matter how vast, no matter how long it rained, releases its entire substance in a last burst of light before vanishing. Nothing is kept. Nothing is hoarded forever. Even the greatest fortresses of darkness open their gates at last and return what they held to the cosmos that made them. The universe, in the end, keeps nothing locked away. Everything that was sealed is, eventually, unsealed. Everything hidden is, eventually, released. And now we arrive at the final stage, the last and longest and quietest of all the ages of the universe. With the black holes gone, there is nothing left to make anything happen. No stars, no remnants, no matter, no black holes. Only the thinnest imaginable scattering of particles, drifting through a space grown so vast that the distances between them defy every scale we have ever known. A few stray electrons and their antimatter partners, a haze of neutrinos, those ghostly near-massless particles passing endlessly through the void, and photons, particles of light, but light so stretched and cooled by the expansion of space that they carry almost no energy at all, colder than the coldest cold, fainter than the faintest faint. This is the dark era, and it does not end. It simply continues, forever, into a future without limit. Let us sit for a moment in the dark era, gently, because it is where the story of the universe truly comes to rest. Imagine the emptiest room you have ever stood in, and then empty it further. Remove the walls, the floor, the air, remove the light, remove everything, and then stretch what remains across distances so enormous that a single particle might drift for spans of time longer than the entire previous history of the cosmos, without ever encountering another. That is the dark era. It is not a place of violence or catastrophe. There is nothing left to be violent. It is a place of perfect, absolute stillness, a cosmos that has finally run all the way down, spent every source of energy, played out every process, and settled into a state of unchanging calm. Physicists have a name for this final state. They call it heat death, though the name is a little misleading because there is no heat left to speak of, only the faintest possible warmth spread so evenly and so thinly that it might as well be cold. What the name really points to is a deep idea from the study of energy and change, the idea of entropy. Entropy is, in a sense, a measure of disorder, or more precisely, a measure of how evenly energy is spread out. And there is a profound law of nature which says that, in any closed system, entropy tends always to increase. Energy tends always to spread from where it is concentrated to where it is not, from hot to cold, from ordered to disordered, from lumpy to smooth. A hot cup of tea in a cool room always cools down, never heats up, its warmth spreading out into the air until everything reaches the same temperature. And once everything is the same temperature, once the energy is spread perfectly evenly, nothing more can happen. There is no longer any difference to drive change, no flow of energy from one place to another, no way to do anything at all. The dark era is the whole universe reaching that final, even temperature. Every concentration of energy that ever existed, every star, every black hole, every remnant, has been spent and spread and smoothed out across the immensity of space. The energy is all still there, in a sense, for energy is never truly destroyed, but it is spread so thinly and so evenly that it can never again gather, never again concentrate, never again light a star, or warm a world, or drive a single event. The universe has reached maximum entropy. It has reached equilibrium. And equilibrium, on this cosmic scale, means the end of happening itself, not the end of existence, for the universe is still there, still real, still expanding, but the end of events, the end of change, the end of the story, not because the pages have run out, but because nothing new will ever be written on them again. This is why heat death is sometimes called, more gently, the Big Freeze. Not because the universe becomes cold in any dramatic, icy way, but because it settles into a final, frozen sameness, a state so uniform and so still that time itself begins to lose its meaning. For time, in a deep sense, is measured by change. We know that time is passing because things happen, because the tea cools, because the star burns, because the clock ticks and the heart beats. But in the dark era, nothing happens. And in a universe where nothing happens, where nothing ever changes, what would time even mean? The particles drift, the space expands. But there are no events to mark the passing of the ages, no clocks, no rhythms, no before and after that make any difference. The universe simply is, endlessly, unchangingly, a vast, dim, silent expanse settling into an eternity of rest. And that, according to our best understanding, is how the universe most likely ends. Not with a bang, but with an endless, gentle fading, not with fire, but with a slow cooling toward stillness. Not in a single catastrophic moment, but across spans of time so vast that the whole bright, busy history of stars and worlds and life is only the tiniest opening flourish, a brief flare of warmth and light and activity at the very beginning of an almost infinite calm. The universe does not die violently. It grows quiet. It spends itself, slowly and completely, and then it rests. There is a peace in that ending that I find genuinely comforting, and I hope you might too. The universe does not end in terror. It ends in tranquility. Everything that ever burned burns itself gently out. Everything that was ever concentrated spreads itself softly thin. Everything that was ever held tightly is finally released, and the cosmos, having done all it will ever do, having made every star and every world and every mind it will ever make, lies down at last in a stillness beyond disturbance. If there is a way for a universe to fall asleep, this is it. And we, sitting here near the very beginning of it all, in the warm, bright morning of cosmic history, are in a sense watching the whole vast day stretch out ahead of us, all the way to a distant and peaceful night. But I would not be honest with you if I told you that the slow fade into the dark era is the only ending our theories allow. It is the most likely ending, the one our best current measurements point toward. But the universe is subtle, and there are other possible endings, other roads the story might take, depending on things we do not yet fully understand. And some of them are stranger, and some of them are faster, and each of them tells us something worth knowing about the nature of the cosmos we live in. So let us set aside the long, gentle fade for a little while and consider the other ways that everything might one day end. The first alternative is a mirror image of the slow expansion, and for a long time, it was considered a serious possibility. It is called the Big Crunch. Remember the great tug-of-war between the outward push of expansion and the inward pull of gravity. In the slow fade ending, expansion wins, driven onward by dark energy, and the universe spreads apart forever. But imagine, instead, that gravity were to win. Imagine that the expansion of the universe were to slow and stop and then reverse. The galaxies, having drifted apart for billions of years, would begin, ever so slowly, to drift back together. Space itself, having stretched for eons, would begin to contract, and over immense spans of time, the whole process of the Big Bang would run backward. The universe would grow smaller and denser and hotter. The galaxies would crowd together and then merge and then dissolve. The cold dark of the far future would give way once more to warmth, and then to heat, and then to a searing, blinding brightness, as all the matter and energy of the cosmos rushed back together toward a single point, collapsing at last into a final, fiery, infinitely dense moment, the mirror of the beginning, the Big Crunch. It is a dramatic ending, almost operatic, the universe collapsing back into the same kind of state from which it emerged. And for those who find the slow, cold fade a little lonely, the Big Crunch can seem strangely appealing, a return, a homecoming, a closing of the circle. Some have even wondered whether such a crunch might not be a true ending at all, but a doorway, whether the collapsing universe might rebound at the last instant and burst outward again in a new Big Bang, beginning the whole story over, a fresh cosmos rising from the ashes of the old. This is the idea of a cyclic universe, a cosmos that expands and contracts, forever, each cycle a new act in an endless play, each ending also a beginning. It is one of the oldest and most poetic ideas about the fate of everything, the notion that the universe breathes, in and out, world without end. But here is where the discovery of dark energy changed the story. For the Big Crunch to happen, gravity would need to win the tug-of-war, and for that, the universe would need to contain enough matter, and dark energy would need to behave very differently than it appears to. Instead, we find the opposite. The expansion is not slowing toward a halt. It is accelerating. driven ever faster by the mysterious push of dark energy. And an accelerating expansion does not reverse. It does not turn back. The galaxies are not slowing in their flight, gathering themselves for a return. They are racing apart faster and faster, with no sign of stopping. So as beautiful as the Big Crunch is, as satisfying as its symmetry may feel, our best measurements suggest it is probably not the ending that awaits us. The universe, it seems, is not going to collapse back into fire. It is going to spread out into stillness. The circle, most likely, does not close. And yet, our understanding of dark energy is far from complete, and that incompleteness opens the door to a stranger ending still, one that is the very opposite of the gentle fade. What if dark energy is not constant? What if, instead of holding steady as space expands, its push grows stronger and stronger over time? This possibility has a name, and the name alone tells you something of its character. It is called the Big Rip. In the slow fade ending, dark energy pushes the galaxies apart, but it acts only on the largest scales, on the vast distances between galaxies. Within a galaxy, gravity still holds the stars together. Within a solar system, gravity still holds the planets in their orbits. Within your own body, the forces between atoms still hold you together, quietly and reliably. The gentle push of dark energy is far too weak to overcome these local bonds. It separates galaxies, but it leaves everything smaller intact. That is the ordinary picture. But in the Big Rip scenario, dark energy grows stronger with time, its push intensifying without limit, until eventually it becomes strong enough to overwhelm not just the space between galaxies, but the bonds within them, and then the bonds within solar systems, and then, at the very end, the bonds within matter itself. Imagine that ending unfolding. First, the accelerating expansion tears the galaxies apart, ripping the stars away from one another, scattering them into the widening void. Then, as the push grows stronger, it reaches inward to the solar systems, pulling planets away from their stars, unbinding the neat clockwork of orbits that had held for eons. Then, stronger still, it begins to tear apart the stars and planets themselves, pulling them to pieces. And in the final moments, in a last frantic acceleration, the expansion grows so violent that it overwhelms even the forces that hold atoms together, ripping apart the very fabric of matter, until every particle is torn from every other, and space itself expands so ferociously that nothing can remain bound to anything at all. The universe does not fade gently into stillness. It flies apart, faster and faster, until it rips itself to shreds. That is the Big Rip. And unlike the slow fade, which takes numbers with 100 zeros, some versions of the Big Rip would arrive far sooner, in perhaps some tens of billions of years, not so very much longer than the universe has already existed. I want to be careful here, and gentle, because this is a more unsettling picture than the peaceful fade, and it is late, and you are resting. So let me reassure you, the Big Rip is a possibility, not a certainty. It depends on dark energy behaving in a particular, extreme way, growing stronger without limit, and our current measurements do not clearly favor that. They are more consistent with a steady dark energy, the kind that leads to the slow, gentle fade. The Big Rip is one of the wilder branches of the story, a road the universe might take, but probably will not. It is the sort of thing worth knowing about, worth marveling at from a safe distance, the way you might read about a storm at sea from a warm and quiet room. It is not something bearing down upon you. It is simply one of the shapes that an ending could take, held up alongside the others, so that we can see the full range of what the cosmos might do. There is one more possibility I want to share with you tonight, the strangest of them all, and then we will return to the gentle fade and let the story come to rest. This last possibility is not about the slow running down of the universe, nor about its expansion tearing it apart. It is about the deep foundations of reality itself, and whether they are as stable as they seem. It is called vacuum decay, and it rests on a subtle and beautiful idea. Recall that empty space, The vacuum is not truly empty. It carries a faint energy of its own, the same energy we have been calling dark energy. Now, our theories suggest that this vacuum energy sits at a particular level, a particular value, and for the universe to be stable, that value ought to be the lowest it can possibly be, resting at the very bottom of its range, like a ball settled at the bottom of a valley. But what if it is not truly at the bottom? What if the vacuum of our universe is resting not at the lowest possible energy, but in a kind of shallow dip partway down, a false bottom, a state that seems stable, but is not truly the lowest it could reach? Physicists call such a state a false vacuum, and a false vacuum, given enough time, could in principle find its way to the true bottom, releasing energy as it settles, the way a ball perched in a shallow dip might, if nudged, roll onward to a deeper valley below. If that ever happened, if the vacuum of our universe were to decay to a lower, more stable state, the consequences would be absolute. At some random point in space, at some random moment, a tiny bubble of true vacuum would form, a bubble in which the laws of physics settle to their deeper, lower energy configuration. And that bubble would expand, its edge racing outward at nearly the speed of light, swallowing everything it touched. Within the bubble, the fundamental constants of nature, the strengths of the forces, the masses of the particles, all the delicate settings that make atoms and chemistry and stars and life possible, would be different and almost certainly hostile to everything we know. Matter as we understand it could not exist inside the bubble. It would sweep across the cosmos silently and invisibly, giving no warning, for it would arrive at the speed of its own light and rewrite reality as it passed. It sounds terrifying, I know, when you first hear it, but let me wrap this one too in the calm it deserves, because there is real comfort hidden inside it. First, we do not know that our vacuum is false. It may be perfectly stable, resting truly at the bottom, in no danger of decaying at all. The measurements are uncertain, and the theories are incomplete, and there is genuine debate about whether this is even possible. Second, and more soothingly, if such a decay were ever to occur, it would give no warning and cause no suffering. Arriving at the speed of light, it would reach you at the very same instant as any possible sign of its coming. There would be no fear, no waiting, no moment of dread, simply an existence, and then, seamlessly, not. And third, and perhaps most reassuring of all, the timescales involved, if it happens at all, are once again so enormous, so far beyond any human or even cosmic span we care about, that it belongs entirely to the realm of the abstract. It is a curiosity of the deep laws of nature, not a shadow over your night. You are as safe from vacuum decay tonight as you are from the fading of the last red dwarf, which is to say, entirely. So there they are, the possible endings, laid out gently side by side. The slow fade into the dark era, the most likely of all, in which the universe spends itself across spans of time beyond imagining, and settles at last into a vast, cold, peaceful stillness. The big crunch, in which gravity reverses the expansion and draws everything back into a final fire, an ending our measurements now make unlikely, but which lingers as a beautiful idea, perhaps even a doorway to rebirth. The big rip, in which an ever-strengthening dark energy tears the cosmos apart from the largest scales down to the smallest, a wilder road the universe could take, but probably will not. And vacuum decay, in which the very foundations of reality shift to a deeper state, rewriting everything in an instant, a strange possibility resting on physics we do not yet fully grasp. Different roads, different shapes, but every one of them lying so unimaginably far ahead that between here and there stretches essentially all of time. And most likely, as I have said, the road the universe walks is the gentlest of them all. The long, slow, patient fade, the stars burning out one by one across trillions of years, the remnants cooling and dissolving across spans with dozens of zeros, the black holes reigning in the dark, and then, at last, releasing everything they held in a final flash of light. And then the endless calm of the dark era, the universe at rest, its work complete, its story told, spread thin, and even and quiet, across an eternity without events. That, above all the others, is where the evidence points. That is how the universe will most likely, finally, end. Now let us leave the far future behind and drift back, slowly, across all those eons, back through the death of the black holes, back through the dissolving of matter, back through the age of remnants, back through the fading of the stars, back to the bright and crowded present, back to this small warm world, back to this room, back to you, resting here, near the very beginning of the story. And let us ask, gently, what all of this might mean, not for the far future, which needs nothing from us, but for us, here, now, tonight. Because there is a question that always seems to arrive, quietly, when you sit for a while, with the ending of everything. If it all fades in the end, if every star burns out, and every trace of warmth spreads thin and even across the void, if the universe is destined for a stillness in which nothing that was ever done leaves any lasting mark, then what is the point of any of it? What is the point of the stars, of the worlds, of the long, slow labor of life, if the final chapter is only silence? It is an old question, and a heavy one, and I do not want to pretend it has an easy answer. But I do want to offer you a gentler way of holding it, one that might sit more kindly with you as you drift towards sleep. Consider that the value of a thing is not always measured by how long it lasts. A sunset does not become meaningless because it fades within the hour. A piece of music does not become pointless because the final note falls silent. A single day at the shore, the sound of the waves, the warmth of the sun, the company of someone you love, is not made worthless by the fact that evening comes. If anything, the ending is part of what makes such things precious. They are gifts precisely because they do not last, moments held all the more tenderly because we know they will pass. The universe, too, is a kind of sunset, an extraordinarily long one, stretching across billions and trillions of years, but a sunset all the same, a passing arrangement of warmth and light and motion, luminous exactly because it is temporary. And consider, too, how astonishing it is that any of it happened at all. Out of the fiery beginning, out of the expanding dark, the universe did not have to produce stars. It did not have to produce galaxies, or planets, or the delicate chemistry of living things, or minds capable of looking up and wondering. But it did. For a long, bright stretch in the middle of its history, this cosmos filled itself with light and gathered that light into worlds. And on at least one of those worlds, the light learned to think and to feel and to ask questions about its own beginning and its own end. You are part of that. You are the universe, briefly, improbably, become aware of itself, looking back across its own vast story and forward to its own distant rest. That the fade comes at the end does not erase the wonder of the middle. If anything, it deepens it. To be here at all, in the age of stars, in the age of light, in the one narrow window when the sky is full and the galaxies are still close enough to see, is a piece of extraordinary good fortune, a gift you did nothing to earn and could never have expected. There is something else worth resting on, as the numbers fade and the mind grows soft. Nothing in the universe is truly lost. This is one of the quiet consolations that runs beneath the whole story of the ending. Energy is never destroyed, only spread, only transformed, only passed from one form to another. The warmth of a star that dies does not vanish. It flows out into space. It lingers in the remnants. It drifts as radiation across the eons. The matter of your own body was forged in stars that died long before the Earth existed, and one distant day, when the Earth and the Sun are gone, those same atoms will drift on, part of the universe still, part of whatever comes next. Nothing is deleted. Everything is carried forward, changed, dispersed, but never erased. The universe does not throw anything away. It only rearranges, endlessly, until at last it comes to rest. And even that rest is not a destruction. It is a settling, a smoothing, a coming to stillness of something that was never truly lost. only spread out too thin and even to gather again. And so the ending, when you sit with it long enough, begins to feel less like a tragedy and more like a completion. The universe does everything it is ever going to do, and then it is done. It makes every star it will ever make. It lights every world it will ever light. It gives rise to every mind that will ever wonder. And then, having done all of it, having spent itself utterly and completely, it lies down and rests, keeping nothing, hoarding nothing, releasing everything it ever held. There is a kind of generosity in that, a kind of grace. The cosmos gives itself away entirely, holding back not a single spark, and asks for nothing in return. It simply shines for as long as it can, and then it rests. I think sometimes that this is why the ending of the universe can be such a strangely soothing thing to contemplate late at night, because it takes all the anxieties of our small and hurried lives, all our worries about time running out, about things not lasting, about the day being too short, and it sets them against a backdrop so vast and so patient that they soften and quiet and lose their sharp edges. The universe is in no hurry. It has all the time there is, and more. It will take 100 trillion years just to burn out its stars, and numbers with 100 zeros to evaporate its black holes. And it does all of this without rushing, without striving, without any anxiety at all, simply following its nature, one slow age after another, in perfect and unbothered calm. There is a lesson in that stillness, if you want one, and there is also, simply, a place to rest, if you would rather just rest. So let the numbers go now. You do not need to hold them. Let go of the trillions and the googles, the white dwarfs and the neutron stars, the event horizons and the false vacuums. Let them settle to the floor of your mind, like sediment, drifting down through deep water, slow and soft and out of sight. You do not need to carry any of it into sleep. You needed only to visit, to stand for a while at the edge of the longest story there is, and to feel, however faintly, the enormous patient calm of a universe that is in no rush to end, and that will not end for longer than your mind can hold. Remember where you are tonight. You are here, near the very beginning. You are alive in the age of stars, in the bright morning of the cosmos, beneath a sky that still remembers how to shine. Every star you could ever see is still burning. Every galaxy is still close enough to touch with light. The long dusk of the remnants, the deep night of the black holes, the endless calm of the dark era, all of it lies so unimaginably far ahead that it is less a destination than a distant dream, a rumor of an ending that neither you, nor your world, nor your sun, nor your galaxy will ever have to see. You are held, right now, in the warm and crowded present, in the fullness of the age of light, and that is a safe and lovely place to fall asleep. The universe will end, one distant day, far beyond all reckoning. It will spend its light and cool and spread thin, and come at last to a stillness beyond disturbance. But not tonight. Tonight the stars are still burning. Tonight the sky is still full. Tonight there is warmth and light, and the slow, soft turning of a world that still remembers how to hold you. And the ending, when it finally comes, will not be a catastrophe, but a completion, the gentlest possible closing of the longest possible story, a universe that gave everything it had, and then, its work complete, lay down to rest. So let yourself do the same. Let your thoughts grow slow. Let your breathing lengthen. Let the vast, patient calm of the cosmos settle over you like a blanket drawn up in the dark. There is nothing you need to solve tonight, and nothing you need to hold. The universe has all the time there is, and so, for now, in this quiet moment, do you rest easy. The stars are still shining, and they will go on shining, for you, for a very, very long time. Sleep well, and whenever you are ready, the darkness will be here, patient and kind, waiting to carry you gently down into rest.